Welcome to the second lecture. How many participants we have in the Zoom?
11, including 3 of us. 8.
8, okay. Well, we are in the exponential curve. Participation. All right, you're recording?
Yes, yes.
Good. All right, so today here we will have a brief recap of wireless communication through the last part of it, namely the point-to-point MIMO, capacity and transceiver structures. If we are able to cover all of it today, if not, we will continue next week. So this is based on mostly in chapter 8, some content in chapter 7 of the textbook, as well as the appendix. So we will look at the SVT-based transmission scheme for the capacity optimal MIMO, and then we'll look at the generalized MIMO case and cover some special cases, zero forcing, some linear receiver structures, so zero forcing, match filter, and LMMSC, linear minimum square receiver. And then combining that with successive interference cancellation receiver and show that that's in fact the capacity achieving structure, basically the same as joint receiver case, but especially the case without channel state information at the transmitter. So let's start with the MIMO channel. MIMO channel you can represent as an input. We have a input X, it's a vector with transmitting in parallel multiple symbols across multiple antennas. They propagate over MIMO channels, and then we have a received signal. So we can go here. An example, let's say, consider a say 2x2 scenario. We have the input from the left, from the right, with x1, x2. There we have the MIMO channel. We can collect all these entries, h11, h22, antenna 1, 2, antenna 1, 2, h21, and h12. So we can collect them into a matrix. Then that's how you define this. Call this h12 and h21. So this here corresponds to the first transmit antenna. This channel vector corresponds to the first transmit antenna. The second transmit. Y2. We actually have here now independent noise, like N1. So we have a system of equations. Right? So Y1 is basically x11 times x1 plus h21 times x2 plus n1. And y2, h1 2 1 plus h2 the system of equations, and we can simply represent this in matrix form. Okay. System of equations. So basically, how to solve this x? If we have a system of equations, y equals hx plus n, ignore n. How would you solve x? Anyone?
You compute the inverse.
Inverse, right? Of course, if it's a square matrix, you just multiply with h inverse on the left. In general, you multiply with the pseudo inverse. Pseudo inverse, which is h permission h inverse the permission, right? And you plug in, and you multiply with the from the left with the h in pseudo inverse, you get h permission h inverse h permission. You can see that clearly this part here is identity, right? And please recover x. Without noise, this would be exactly the x. With noise, it's distorted by this term. So what are the conditions that this works? What's the condition for h that we have that we can resolve x? How many lines versus how many unknowns? Basic linear algebra. What are the dimensions of h that we have a solution? Given the number, given that the size of the transmitted vector, what would be the size of the
Antennas has to be at least equal to the number of antennas.
yes. NR has to be larger or equal to NT. You can see from here, this inverse, this has to be invertible, right? Meaning that H permission H has to be full rank. It's full rank only if this condition holds. If we are transmitting more streams than we have receive antennas, we have interference limited case. We cannot resolve. So we need at least as many receive antennas as we're transmitting streams.
In general, rank of H should be equal to the number of symbols that like streams we are transmitting.
Yeah, of course, rank can be constrained by the radio channel itself.
Yeah, they can be dependent.
But anyway, so when you know the channel, then you can actually adjust the number of streams. The simple solution, of course, if you have more antennas, more transmit antennas, you just choose a subset of antennas. Right? If you don't have any channel information, you can just send from at most NR of NT antennas. But this is the linear structure. But of course, when we go to nonlinear structures, MMS is sick, you can resolve also the overall case, but the corresponding rate will be very small. So the linear structure is close to optimal anyway. Okay, singular value decomposition. So I'm just going quite fast because this is a recap Alice communication tool. If you need to look into more details, you can go to Moodle and check the lectures from WirelessCom 2. Okay, so given any matrix, we can decompose any matrix. We can decompose using singular value decomposition. Right, so we can compose matrix H to be a multiplication of left singular vectors times diagonal singular value matrix and set of right singular vectors. So in MATLAB, it's maybe I can just quickly show. Yeah, I should take this in from the video.
Yes, yes.
Yeah. Okay, let's generate a random matrix. To let's say NR times T is the real part, and then imaginary part. So NR, let's say, is 3. And the four. So now we can generate the general matrix. 4. Where each now when we generate it using complex Gaussian distribution, it means that every between each transmit and receive antennas is IID, right? So this models the rich scattering environment. Okay, then we can just check the how does the SVD work. Right. So just define U lambda P to be SVD of H. So we get the U matrix, which is 3 by 3, L matrix, lambda matrix, which has now 3 non-zero singular values, and then V matrix is 4 by 4. But the last column of the vector corresponds to so-called move space.
Mm-hmm.
Right? And we can recover by U times L times V Hermitian should be the same as H, right? If you like that. So from that example, the dimensions how it works, and also you can one of the property of this SPD is that the singular vectors are unit norm and orthogonal. So when we multiply UHU, then have U times UA, identity matrix. But actually, this doesn't hold in general because we have different sizes of matrices.
Mm-hmm.
Just referring to the fact that they are identity matrices. Okay, so how can we use now this SVD to simplify? We notice that this minor channel is kind of a mess. That it's every received sample at each antenna consists of all transmitted. It's a summation of all transmitted symbols. In principle, it's easy to, if you know the channel, you just invert it and you get an estimate of it. So there's that's clearly suboptimal strategy. Let's see what we can do better. And one way to do it is to use SVD, so the optimal way. So we can start with the minor channel. Is this clearly visible? Okay. Now we can define the transmitted. So previously when we have this, let's say we have 4 transmitters, 2 receivers. X1, X2, X3, X4. Now, in this case, see that our degree of freedom is limited by the number of receive antennas, right? It's the minimum of n sub t and n sub r, which is 2 in this case. So one strategy would be just simply pick 2 antennas out of 4 and assign independent streams, and we could still resolve it using the zero forcing receiver, the inverse. Then we would actually not be utilizing these 2 antennas. So that's something more clever to do. So we can perform so-called beamforming or pre-coding. Instead of sending 4 streams, we know by default that okay, we shouldn't transmit more than 2 streams. Right? So we generate a vector of 2 data symbols. Then we pass that through a power loading, and then through a recoding matrix, right? B1 and B2. And now this recoding matrix actually, so here each of these vectors corresponds to one transmitted symbol. So this recoding vector actually assigns this symbol to each transmit antenna. Both of these symbols are transmitted from all antennas, or superposition of these symbols is transmitted from all antennas, properly weighted with the V vector, so V matrix. And this has this nice property that now when we define X transmitted signal vector to be a precoded, X is now precoded by V and multiplied by a diagonal power loading matrix, and then we assign symbols. Right? So the length of this simple vector should be at most the DOF of the channel, right? 2 this particle. So now we plug that in here, we get H, V. Okay. And now when we follow the structures, the SVD structure, basically what if we now multiply the received signal by the left singular vector matrix U, always by tilde, we get the following. Now we can also write this H as a single value composition. So we have U permission times U times lambda times V permission times V our loading matrix times D, okay, plus UH and tilde. Okay. Now something nice happens. It becomes identity matrix. This is already diagonal matrix. This is identity matrix, diagonal matrix. Okay. Okay. So we can simplify this to lambda square D plus NT. You can see actually that this lambda is now the equivalent channel matrix after pre-processing by V and post-processing by U. It diagonalizes the matrix, channel matrix. We have a diagonal channel. Diagonal channel meaning that there's no interference between D1 and D2. Right? So it's easy. Now we have a parallel channel, so we can process them separately. Okay, you can see that when we plug in here that the power value P square root of P1 square root of P2 and D1 and D2 plus n tilde 1 and tilde 2. This is equivalent. This is the matrix representation of a system of equations. Right? So we have y tilde 1 equals lambda 1 square root of P1 D1 plus n1 tilde 5 2. The received signal going to the equivalent received signal at the output of the received beamformer U lambda 2 P2 plus n2. Okay, so these are parallel, two parallel channels. You can see that we have that mean which is 2 in this case, parallel channel. What can we do with this? We can first compute the SNR per stream. These are parallel channels. We have Gaussian input. And the capacity or the rate of a stream, the Gaussian stream generated from the Gaussian input depends on the SNR, right? So the SNR, signal to noise ratio of the first stream, is simply expectation square of this entire single part over the expectation square or variance of the noise, right? So we have lambda 1 square P1 over N0, right? Noise is generic. Okay, why is this N tilde following the same statistics? Let me, even though it was multiplied by this U Hermitian, let me clarify that. So let's compute the covariance matrix of N tilde. Okay, so we can now plug in the U H N permission U. Okay, U is fixed. We can take the expectation inside. So this is U Hermitian expectation and permission U, right? And we know that covariance of N is independent noise added at the receive antenna has this structure, right? So it's independent. Both of these, both the noise processes at both receive antenna follow the same process, the same variance. Okay. So this goes in front. We have N0 U permission U, and we know that this is identical matrix. So multiplying by this unitary matrix U, multiplying the received signal by unitary matrix U permission does not alter the statistics of the noise. Okay. That's that, and that's why we just have the same noise variance here, right? So we have the SNR for the first stream, lambda 1 square times P1 over N0, and this maps to a rate log 2 plus R1, and similarly for SNR2. And the sum rate is then simply summing up, sum rate over these parallel channels, summing up over I1 to N min log 2 1 plus lambda I square TI N0. Okay, this is the sum rate. It can be computed for a certain power allocation, right? Now the question is that if we have a limited power constraint transmitter, and we have a base station serving a single user. It has power amplifiers that have limited transmit power. If we now assume somewhat unrealistic scenario that there's some power constraint over these power amplifiers, in practice, each power amplifier has its own constraint, so it's the antenna power constraint. It can be handled, but it's a bit more complicated. But let's assume that there's a single power constraint, meaning that the sum over pi is upper bounded by P, transmit power constant. So this allows us to basically arbitrarily allocate any share of power among all these parallel streams. So now we have an optimization problem. We want to maximize with respect to the scalars p, I, this objective, some rate, is the concave function of p. Then you plot log 1 plus x function. It's a function of x, it's a concave function, right? Concave meaning that any two pairs of points, if you connect them by a affine function, the actual function value is larger than any affine combination of these points. Okay. Linear combination. All right. So you have now a of course the powers have to be also positive. So we have a convex optimization problem. In the wireless communication tool, we looked at the conditions, optimality conditions, and came up with this water filling solution to optimally allocate. So this water filling solution, PI, the PI expression can be directly derived from the optimality conditions, writing the Lagrangian, differentiating with respect to P, using these other conditions from the KBT to come up with this set of equations. So you can see that the P, the power, is a function of the inverse of the this equivalent channel gain, eigenvalue, and its dual variable mu, which corresponds to the so-called water level. And this mu is chosen to satisfy the power constraint. So how you can solve this in practice? You can order this inverse values. Okay, these are the n0 over lambda I squared. Okay, and let's assume that we have, for example, 3 streams, right? So this power response is the strongest. It's an inverse, so it's the smallest, and the weakest, right? And a simple way to check to allocate the power is to use so-called water filling, that you are starting to pour liquid into this valley, right? Starting to increase the water level, and now this integral or summation over this area corresponds to the power, right? You can see that if we set the water level here, right, this minus this is the power allocated to the first stream, this minus this second stream. In this particular case, the third stream would not get anything, right? But if this power here, P1 plus P2, happens to be exactly P, is up here, right? And we don't allocate anything to the weakest streams, right? So you can see that if the SNR is, if you have little power available, or if the received signal strength is low, the optimal in the limit, the low SNR limit, you only allocate power to the strongest. And when the SNR is large, your power budget is larger, then you allocate power to all streams. Right? All right, that was the SVD based. Any questions at this point? It's quite clear, I suppose. Okay, let's go to the general structures. So now we have the question of channel state information at the transmit. So we had this long discussion about duplexing yesterday, and we argued that if we have a TDD and properly calibrated TXRX chains and semi-static channel, we can learn the channel from the uplink pilot measurements and use that channel knowledge to design our transmit recorders for the downlink transmission. So ideally, if we have sufficiently high SNR for the pilot estimation, so that the estimation noise can be ignored at the receiver, you can fairly safely choose your precoder to correspond to the right singular vectors of the channel matrix that you have estimated. Because this is something that you don't do in practice. It's always, in practice, the pilots are always precoded. But anyway, that's another discussion. Assuming that the pilots are now antenna specific in uplink, we can estimate if from each base station antenna, we can estimate the channel response from all transmitted antennas and construct the channel estimate at the base station and use that for transmission simply with the SVD processing as we went through previously. But it requires full CSI, full channel state information at the transmit. In the TDD, it comes kind of for free. In the FTD, or when the uplink channel estimates are not reliable due to high mobility, for example, then that CSI might not be useful. Right? In FTD, in rich scattering environment, the channel estimation from uplink is not really useful for downlink. The narrow angular spread, like line of sight scenarios, the statistical properties of uplink and downlink are more or less the same. So you can use the statistical channel knowledge. For example, if you have a line of sight channel, you have no fading, right? The channel becomes deterministic. Basically, acquiring the channel is basically estimating the angle of arrival in uplink, and then using that information for the downlink transmission. Basically, beamforming, single stream beamforming. Okay, but here we have these two extremes. We either ignore it perfectly, and then we use the right singular vectors for transmission, or we don't know it at all. So in this case, the best strategy is to assign independent streams to each transmit antennas, no precoding. The precoder is identity made. So these are the two extremes that we consider. Of course, you can have some statistical knowledge. So if you have statistical knowledge like covariance matrix, then you can take the eigenvalue decomposition of the covariance matrix and choose the eigenvectors of the covariance matrix as transmit directions. For example, in the line of sight case, that would be rank 1 matrix. When you take the eigenvector of that covariance matrix that corresponds to that angle of departure or angle of arrival, right? Okay, in general, capacity of the communication can be expressed in terms of mutual information and this differential entropy formulas, right? Maybe just a little recap. Wireless communication 2, we looked often at this Venn diagram, right? We have Y and X. We have a process. In wireless communication, we started with the Gaussian case. Right? No channel, just noise. But here we can also assume that we have another process called H. But H and X are independent, right? So there's no overlap. They don't have any mutual information because they're independent. In general, when we want to evaluate the capacity of such setup, input X, output Y, we should look at the mutual information between the input and output. So, and the maximizing the mutual information with respect to input and power constraint, assuming Gaussian signaling, can be shown to be the capacity achieving strategy. So we can now consider X, Y, and H to be random variables. We can look at what could be the relation between X and point distribution of Y and H. Right? So we can use in general, we can express if we have a, let's say, Y Z, right? And we want to find what would be the mutual information between X and the joint distribution of Y and Z. We can draw it like this, and we can further split this into two parts by using chain rule of mutual information. So we can express I, X, Y, Z as mutual information between X and Z plus mutual information between X and Z. X and Y given Z, right? The first part would correspond to this one. The second part, this one, right? X and Y given Z. Okay. If they apply it here, Z is now H. You can see that the mutual information between X and H is equal because they are independent. Channel is independent, input is independent. And less mutual information between X and Y, H. Given channel knowledge. Okay, so let's assume for a moment that we have a fixed channel realization. H is known, right? It's just a matrix. It's just no number, complex varied number. So we can now express the mutual information simply as a difference between differential entropy of Y minus differential entropy of Y given X. How can we compute differential entropy of a vector y? So in general, differential entropy of vector Gaussian distributed vector y depends on its covariance matrix. It's something that we covered in that. While communication 2, the log set i.e. covariance of y. What is covariance of y? Simply expectation of y permission. Okay. So what is the covariance of y? So we just plug in the expression y. So we have expectation of hx plus n times hx plus n permission, right? And then we can just expand, assuming that h is fixed. Right? So the first term will be h expectation of x times x permission h, right? Then we have these cross terms, expectation of hx times n permission plus expectation of n x permission h permission plus then expectation of is that just considering all these terms separately. Okay, we can call this covariance matrix of x, kx. What about these cross terms? So x and n are independent. So when we take the expectation, this is a rank 1 matrix, hx times n permission, the rank 1 matrix. But now when you have this random, if they are x and n are independent, when you take an expectation of this random rank 1 matrices, the expectation is 0, right? 0, right? So covariance of y is simply h kx h plus n0 y. So what about the covariance of y given x? Y given x, simply because x is given, known, so this term is cancelled, so it's equivalent to differential entropy of noise, and the covariance of noise is n0i. So this is n0i. So we have this covariance of so h n is log set i.e. n0i. But since this is a diagonal matrix, and determinant of diagonal matrix is a product of diagonal terms, where each term is n0. So it's n0 to power nr.
Phi e n0.
What's that?
Phi e.
Phi e also. So that's exactly what we have. Phi e n0 nr. Equivalent to this one. Now you just plug in these values. Let's just try it once more. So we have visual information between x and y. We have differential entropy of y. We compute it with log that you can take the IE out. We can use the that rule that A times that B is that of A times that of B, right? So we can take first gets out, i.e. I times, and we can apply log of product is log of sum. Right, so we have then log that i.e. I times plus log that h kx h permission plus n0 I minus log that i.e. I minus log that n0 I. Good. These two cancel. And this one goes inside. So log minus log is log of log that A minus log that B is the same as log of that A divided by that B, and then we can take that inside and blah blah blah. So in the end, we have I plus 1 over n0 h kx. That's the general capacity formula to my model. Right? And we can, this is a permission matrix, yes, please.
Why is it less than or equal?
Sorry?
There is the word less than or equal instead of equal. What happened there?
This one. What was the upper bound here?
Upper bound is because of the Gaussian assumption.
Well, yeah. Of course, Gaussianity.
In general,
Yeah, in general.
Y is not Gaussian.
That's true. Yeah. For any other input distribution than Gaussian, we have the strict inequality. Right? Equality is achieved only with the Gaussian input. Yeah, that must be that. Okay, the covariance matrix, Hermitian matrix, we can of course split that using eigenvalue decomposition. Or we can for example using eigenvalue decomposition, we can split the Hermitian covariance matrix to a normalized recording vectors or matrices, and then a power loading matrix. This is something that we will. Okay, let's take a 5-minute break. Put the recording on so you don't get the same. You get just one package.
We pause.
You can pause it. Okay, is recording again? Good. Okay, so this this expression here was given a certain channel realization. So in general, when we have a fading channel, we would need to take simply just to compute so-called ergodic capacity we discussed in detail. Wireless communication 2, we simply need to take an expectation or an average of over all possible channel realizations. That's clear. So basically, if you have a uncorrelated fading process, for example, principle, and you have an average power constraint, then you should have a strategy which is kind of optimized over both space and time, possibly over frequencies. Of course, that's not practical often, and often you have the instantaneous power constraint. So in my setup, this optimization is carried out for each channel realization separately, right? Given this power constraint. So in practice, even though when we're trying to come up with some practical schemes that are close to capacity achieving, the optimization over covariance matrices or powers carried out over a fixed time interval, right? Given a fixed channel. Okay, but this is the definition of the. If you can do this over the whole trading process, is another case. That's something. Average over all channel realization. So when you're plotting actually figures for a minor channel, there also we should actually carry out the optimization over all possible trades. But in practice, what you do is that you optimize the covariance matrices for each channel realization separately, and then compute the ergodic capacity. That's not strictly speaking the optimal strategy, at least over if you have average power constraint. But if you have instantaneous power constraint, that's the way to do it. Okay, if we consider a special case that we have just a single antenna, so this is just to show that everything holds. Then you have a single antenna. It's basically equivalent to single visible antenna. And then assuming that you have independent streams per antenna, doesn't really matter whether these antennas are placed in one device or they are placed apart, right? So it's the same scenario as we have n sub t users, right? It doesn't really matter. We still have a independent power constraint here. Generate independent streams, x3, x2, x1. So we can compute the mutual information for this case as mutual information between joint distribution x1, x2, x3, and y, right? So we have if you think of Venn diagram, y, x1, x2, x3, we are interested in this overlapping area. So you can compute this as h of y. This is now a scalar, so covariance becomes variance. Variance of y minus h of y given x1, x2, x3, which is plot i.e. n0 plus h1 square p1 plus h2 square p2 plus h3 p3, right? And minus well, i.e. n0, right? And in the end you have log 1 plus sum hi squared pi over n0. Okay, if you have n sub t users, and that's exactly like that.
If they all send the same message, right?
But this is without channel state information.
I know, but if they send all the same, they all send the same message. Otherwise, they will cause interference, right? Each other.
This is the summary. Of course, it requires successive interference.
Oh, okay.
Right.
Okay.
Yeah, I'm not talking about the this form here is general. It doesn't assume anything about receiver structure. Receiver structure is not, it's just optimal receiver structure. Joint receiver, right? All the whole X is jointly decoded. We will see that the joint decoder can be implemented as an MMSC SIG receiver, right? So you have the linear front end, and then the successive indefinite cancellation that can provide you the capacity, right? That's just one implementation, but that's capacity optimal implementation. So here as well, we need SIG. Since we have single antenna, we don't have to deform a front end, just single successive indefinite. But this is the sum rate expression. This is the sum rate expression. Capacity over the sum over all these transmitted antenna specific signals. Okay. Just to show that. And you can, of course, you can come up with the same directly. If we start with this expression, let's just consider one channel realization. So we have log the capacity expression. So INR becomes 1 because NR is 1. So let's replace this one plus 1 over N0. Now H becomes 1 times NT vector. So we have H row vector, right? H row vector is now H1, H2, H3, and so forth, right? For 3 transmit antennas times Q. Okay. Obviously, if you look at this closer, you have H1, H2, H3 times identity matrix I111 times H1 complex conjugate, H2 complex conjugate, H3 complex conjugate. Okay. This times this is simply
By identity.
I'm missing some.
It needs not to be identity. It can be
Q is I. Okay, sorry. So KX is QPQ. Okay. So KX is now then I times T over NT, T over NT, T over NT, diagonal matrix times I. Okay. Now it's good. So here we plug in the P, P2, P1, P2, P3. Okay. Very good. Then this is equivalent to sum of HI. Good. Okay. So in general, as I mentioned earlier, the transfer covariance matrix, even in the if you have CSI only at the receiver, you should design, if you know something about the statistics, covariance matrix of channel, you should use that to design the transmit directions Q. Right? For example, if you have if you know the covariance matrix, you can use eigenvalue decomposition of the covariance matrix and use the eigenvectors as transmit directions. The power loading is more complicated. It's not water filled, but there's some beyond the scope of this course, or it's not so interesting. Or it is interesting, but fun.
Mhm.
I don't have it here. Okay, but then now if we assume the extreme case that the channel is IID, right? So basically, covariance matrix of H is identity matrix, right? So then the optimum strategy is to make covariance matrix identity matrix, just like here. It's just power loading. And since we don't know anything about the channel, the best power loading strategy is equal power loading over all antennas. Right? That's what it means. So for each antenna, we have equal power. So we have total power budget is P, so each antenna gets P over NT. Okay, so now when we plug in the KX here, it's a diagonal matrix. Then we have this simplified expression. And again, when we plug in the SVD expression, so this one here we can express as log that I plus P over NT0 U lambda the emission, then H emission is equal to V times lambda U emission. This is your identity matrix. And then again we can use this net rule that if you have determinant of I plus A B, it's equivalent to I plus B. Okay. And we declare, for example, this one to be A and this one to be B. We can move this one over here. So the dimensions may change depending on, but doesn't matter. This identity matrix might have a different dimensions if H is not square. Right? But it doesn't matter that it's the holds. By the way, if you are, there's a nice Wikipedia page. It's a type determinant of matrix or something. You will find all these determinant rules. Okay. So lambda U revision U lambda identity. So we have a determinant of a diagonal matrix again. Right? I plus P over NT N0 lambda, right? And again, if we have a determinant of a diagonal matrix, it's a product of diagonal terms. And when we take the log of product, it's a sum of logs. Right? And we get this. And if we further want to take the expectation or ergodic as the expectation over all possible realization of H. And that's it. That's the capacity of the case without channel state information. CSI just complementing that. It's SVD solution. So now we know that, okay, when we know the CSI, the Q should be chosen from that to be the right angular vector of the channel matrix, V, and then we have the P as the power loading matrix. And now when we plug in, we have this expression over single channel realization. I plus 1 over N0 H of n times kx of n times h of n remission. Again, using the SVD, I plus 1 over n0 u lambda v remission, and plug in the kx, v, p, v remission, and then remission of h, it's SVD, u lambda v remission. Okay, there's a lot of this one here is identity matrix, and then we can use again the same rule as previously, that I plus AB plus that I plus BA. So this one here can be
Kx is V.
sorry, this is okay. These views are too close to each other. Okay. Right. So they cancel each other. And we have log get I plus P matrix times lambda matrix. Now, optimization there. Okay, now we have to also add these time indices. Okay. So this one you can write equivalently as sum of log 1 plus lambda I of n times p I of n over n0
Lambda square.
square and square here. So, and when we have the expectation here in front, and we have an average power constraint, so you can see that the power optimization now becomes over time and space, right? You have to find a water level that satisfies this ergodic power constraint, average power constraint. Okay. This can be difficult. It can be pre-computed if you have a stationary trading process. The statistics doesn't change, so you can safely choose a fixed value that on average meets the power constraint. Right. If you have large number of antennas, and there's a lot of diversity, actually the fluctuation of instantaneous power, the more antennas you have, if you follow this strategy, the closer the average allocated sum power would be the instantaneous. So closer the instantaneous sum power across streams would be to the average power over time. Okay. So that's why it's not really important to. I mean, you don't lose much in the optimization instantaneously, assuming even if you are able to allow this kind of fluctuation, if you have average power constraints, so instantaneous power could go above or below the average power constraint. So you are not constrained instantaneously by a certain fixed limit. Even in that case, you don't lose much if you have enough degrees of freedom using just a fixed power, instantaneously fixed power. Maybe that's a good homework. We can see, we will see. Okay. Another interesting, skipping, just selected the interesting subset of material from wireless communication 2. One interesting special case is so-called massive MIMO, because that's a hot topic nowadays. The number of antennas is ever increasing. When you go to higher frequencies, you need to increase the number of antennas to overcome the increased path loss by directing or focusing the transmitted power to a point in space. And therefore, it's interesting to see what happens. There are two scenarios: that number of antennas increases while keeping the number of streams fixed. Right? We have that case also covered. Another interesting scenario is to consider a case where both number of antennas and streams increase with the fixed ratio. When we have the latter scenario, so basically the rank of the matrix increases with the same speed with the size of the matrix. Right? So when we have such scenario, things become deterministic. So when the matrices become large, we can apply so-called random matrix theory to analyze the behavior. We can always use the matrix, random matrix theory to get an approximation of a finite size matrix, and the approximation actually becomes fairly accurate, as we will see, even for fairly modest size matrices. Okay, so this is a special case when we have a square channel, square scenario. Number of transmit antennas equals number of receive antennas, right? So we are transmitting n streams, and assuming that the rank of the matrix is n, it's an INT. We can of course handle other scenarios that we have a fixed ratio between MT and NR, and similar results apply. But let's consider just this simple scenario first. Right. So in this case, of course, we can plug in here the and in this case, we assume that in the highest NR, especially, the equal power loading is asymptotically optimal, right? So here we assume that this power is equally divided over n dimensions, right? SNR over n is the power allocation per eigenmole, right? You don't lose much, but you don't lose anything asymptotically, right? Using the equal power loading in this scenario, assuming equal power loading. Okay? But we can also interpret this now differently, that we have the SNR, unnormalized SNR, but then normalized channel. So we are basically normalizing the H emission by n, right? So when the n and the size of H increases, it's normalized by n, right? So I mean, if you're generating H from like every entry or from IID distribution, when you look at the trace of H Hermitian, it keeps increasing with n, right? But now we normalize it by n, so it does not increase. The trace does not increase. So now you can also consider this as an eigenvalue, or lambda over square root of n to be the singular value of the normalized matrix H, right? This is the other way of interpreting this. Now, but this is very important. We need to normalize the channel to be able to study its behavior in the limit. So now, if we start to generate, maybe I could even show in MATLAB, I have this page expression. Let's consider a scenario first. Let's say nt equals 8. Then r equals 8. Then we have 8 by 8. Then we simply take the SVD of h. If we just take SVD of h, we get the similar values. Okay, but let's normalize. Let's normalize the values by use the normalized stage. Then we can take histogram of can you see this? Is it well visible in the?
Yes.
Okay. Let's see what happens. Something is happening. Hmm. 10 equals okay. N beings. Okay, I'm improvising, so let's see.
This is only one time realization.
No, but I'm just
Make h bigger.
it should become
H big.
make page really
Yeah.
large.
But previously there are only 8 values. So
Yeah. Okay. They should start. It's in his. Yeah. Let me see. I've done this before, but I don't remember how. Let's experiment. So. No,
Didn't change the edge.
Okay. All right. Now we start. Try 20. Okay, you can see that it starts to have some kind of a shape. Let's try 1,000 numbers. Then generate a page. 1,000 by 1,000 matrix. And histogram. Okay, very quick. Right? It starts to look more deterministic. The histogram of this singular value with this granularity of 20. We can increase the granularity to 100, for example. And this. Start to believe? Let's try 10,000. over flow. All right, 10,000 was too much. 1048. Oh. Oh, I completely stopped. That was a mistake. Big mistake. Okay, so it's done. Well, if the generation of age took so long,
Yeah, history is also.
to be there, let's do it. Okay, how is that possible?
I guess you have killed it.
It might
Little
have
bit.
been, yeah.
Check this
But
out.
anyways, you get the point. You can try it home. There. But you can see the same behavior. 32, 164, and 128. Now, when n goes to infinity, the distribution can be approximated by so-called quarter circle law. So the distribution of normalized channel, the distribution of these normalized singular values becomes deterministic. The simple formula just follows this expression, and it's valid when the normalized lambda I over square root of n, which is x here, is between 0 and 2, meaning that the square root version is between 0 and 4. Sorry, the square root version is between 0 and 4. So now we know the distribution of this one, right? So if you think about normalized, so this would be the sum rate over n streams. Now if you normalize it, so basically divide the sum rate over n, so this would be the stream, this would be the rate per stream. Okay. So you can also now interpret this as an expectation. When n goes to infinity, this becomes expectation. And expectation, when n goes to infinity, we notice that the distribution of this becomes deterministic. So we can replace expectation with an integral over the distribution, the probability mass function of that one, right? So now we have just x, which is the squared singular vector, normalized singular vector, and then this is the corresponding probability mass function, right? This is the definition of expectation for continuous with the known distribution on PNF. And this gives you the capacity, the normalized capacity per dimension. So if you just plug in this quarter circle formula from here, integrate over x, you get closed form solution. Integrate over x over 0 from 0 to 4, you get the closed form expression of c. That depends only on the x and r. Right? Quite nice. So to get the sum capacity, you simply multiply by n. Of course, this comes with an assumption that n goes to infinity, right? So when you apply this to any finite dimension, it's an approximation, right? It doesn't hold exactly. It only holds. So now you can use this value here, for example, with some finite values. Here we have simulated with n equals 2, 4, and 8. You can see that with 8 antennas, 8 transmit receive antennas. The expected ergodic capacity, now this is an ergodic capacity over large number of channel realizers. You cannot really distinguish between the approximation and the actual ergodic capacity computed by averaging large number of channel realizers. Even for 2 antennas, there's very small difference, but that's for the ergodic capacity. For the for the instantaneous capacity, there's large variation here, but less here, right? But anyway, it's just to show that there are nice tools available too, and we have used it in. I have one student who talked a lot on this, and we applied to quite practical problems. And you can, if you have something, we have design parameter, which is a scalar that depends on large matrices. You can get nice resource allocation without needing to invert large matrices. You can use the properties of the random matrix theory to come up with approximate solutions that are amazingly accurate even for relatively small number of dimensions. Okay, let's consider another scenario. The case when we don't know the channel at the transmitter, but the number of receive antennas is much larger than the transmit antenna. So we should have in practice, this could correspond to massive MIMO scenario. We have a base station, and then we have this planar array. And we have, of course, in the high, you recall from these examples that we discussed yesterday that if you have, for example, 200 cross-polarized entries, 2 gigahertz, you need 1.5 meter times 75 centimeter planar antenna array. But if you go to 10-fold higher, 20 gigahertz, just 1/10 of the size, right? So it's very small. Anyways, think about, let's say, 400 antenna elements here, and let's say UE with 2 antennas, right? So you have large disparity between number of receive antennas and number of transmit antennas, right? Now, if you consider the capacity, and we don't have CSID, but actually here the CSID does not really matter. And we assume that this is an IID channel, so there's a huge scatter rate around. Of course, in practice, this is not the case. So we have P over NT N0 times H emission. Okay. So you can see that this is in fact now, let's say 400 by 400 matrix. But what's the rank of this matrix? This particular case. What's the rank of H times H emission? 2. Right? So we can actually use the log rule I plus AD to be I plus BA. So we can. So now this would be NR dimensional equivalent to log I plus N I of NT plus T over H emission H. It's equivalent. You can check if you don't believe. So now we can move this one here as a normalizing factor, right? So P over NT over N0. So we normalize this H emission H by NT. and look at the properties of this. So when the NR becomes much larger than NT, the normalized version of H remission H becomes diagonal. We can check this also very quickly. MATLAB. Let's make NR, let's say 1000, and NT 2. Then we generate the H. And then we look at the H remission times H divided by R. Let's do something. Divided by
It's an R, the large N.
Yes. Where?
Otherwise it will grow.
It's not identical.
An R, yeah,
Almost.
almost.
It's a mistake here. Okay, but you can say when you divide, when you normalize by NR. Okay. Okay, just a trick. Okay. So we can add here NR and NR, right? So they cancel each other. E times NR, NT, N0, H remission, H NR. Now this becomes normalized by NR, that is NR term. And that's the B forming game. Okay. All right. So this becomes identity matrix, and you can approximate this one with, because it's an identity matrix with n sub t, not identity, diagonal matrix with n sub t times n sub t diagonal matrix. So which are all identical. So it's, you can take the n sub t exponent in front, and you have +1 plus b times nr over nt and c. So you have nr for B forming, meaning that the match filter is asymptotically optimal. It's quite intuitively, it makes sense because you generate two large vectors and take an inner product between those two vectors and normalize it by nr. The inner product is close to 0. Goes to 0 when nr goes to infinity. They are independent. Okay, the same applies to the visual scenario when n sub t is larger than nt. Of course, you need the CSI detail. But let's continue tomorrow. Sorry, next week, Tuesday at 10. Then we will cover the rest of this slide set and move on to multi-user MIMO. And please read the book, start reading chapter 10 beforehand, so it's easier for you to follow the lecture. All right.
Is there any exercise?
Exercise session, we have to decide. Let's discuss actually after this. We will inform them. So maybe towards the end of next week, we might have already, or the following week. We will see. The thing is that you need to have covered the material, obviously, before you're able to.
There is no session.
Currently, that's a good point that you thought that. Currently, those exercise sessions are not scheduled in Moodle, and we don't want to waste these scarce lectures for exercise. Sorry to say waste, but we can schedule them separately. Okay, and you can decide whether you want to have an in-class exercise session, or we can have it also virtual or Zoom. Any preference?
Or pre-recorded.
Or pre-recorded. Well, let's not go for the pre-recorded because it's good to have some face-to-face feedback. Would you like to have? Well, I guess the ones in Zoom would like to have. Anyways, it has to be hybrid. Okay, but I suppose all of you who are already here could also come to the exercise sessions, right? Okay, so we will any particular constraints when it comes to dates? Would Friday be fine?
There is another class, is like actually matrix analysis course, and actually is interfering with the exercise class. So if it would be like on another day, it would be better. So, and even like the main lecture, like on YouTube, actually are interfering with that course. So
okay. Well, that's not much we can do because they have because that's maybe planned for. Because this is actually kind of a second year course. Of course, it's a bit unfortunate because this is organized every 2 years, so it's a mix of students. Also, we have PhD students and first and second year master students. So it's difficult to find time slot unless we want to come here in the evening. Let's not touch the lecture times. But the exercise times, are there some restrictions if we allocate that for Friday? Friday afternoon, okay. Nothing, okay. So let's. Sorry.
If you're changing it to Friday, maybe not between 12:30 and 1.
Sure, yeah. In the afternoon, yes. Or Monday or whatever. Well, a Friday afternoon after. Okay. Thank you. And, see you on Tuesday.